Hello, welcome to the first video on writing a code in Verilog in Xilinx. And in this video, as this is the first one, let's get started with a small basic half adder. Let's write a Verilog code for half adder, and the process is same. Initial steps: select a new project and write a name here. HAA. I will write ha. And now observe this, that is product category all Spartan 3 XC3S200 FT256 and ISC simulator speed grade -4 and click on next and click on next until finish, and you will be obtaining with this a blank window. And now you have to add a new source, that is a Verilog module, and now you have to write here HAA. Now I'm going to add this to the project, and I don't write here because I want to mention all the inputs and outputs that I'm going to write in front of you before in the module section itself, after explaining what actually it is. So instead of directly writing a code for a half adder, first of all one should know what actually half adder is, and if you know that and the circuit diagram of half adder, then you can write the code for the half adder in any way you want. So first let's discuss about the half adder. These are the slides that was prepared by me. So convinced with this. If you're not convinced, you can comment in the comment section. And according to me, what actually half adder is, it is used for a single data bit addition. What you're thinking? Wait, stop there. I know that you all thinking, what, we add 2 bits, then why I use the term single bit addition. I got that point. And now what I'm going to say is, this is the precise definition. Precise definition can be explained as follows. Why? Because the other bit can be considered as a carry bit, and depending on the carry bit and the input bit, the output of the half adder will be obtained. And if you want to get for a full adder, then what you have to do is, to get for a full adder, I'm going to write here for addition of more than 1 bit. Like suppose for 2 bits we got an update of a full adder, so this is used for a more than 1 bit data. So from this we can say that it is a half adder, means a single bit data addition. In that context or in that point of view, I use the term that it is a single bit addition. Now the other bit can be called as carry bit. Now this is the truth table for half adder. Now let me explain how we obtain with this. So if the data bit is 0, then there are 2 possible cases for the carry, that is 0 and 1 for the data bit 0. So this is my carry in. I can take it as B for ease of writing. And for the data bit 1, again there are 2 possibilities for the carry, that is 0 and 1. You can write this or you can interchange these two, no problem, that's not a big deal, because even though the sum and carry will not change. Now we can write this as 0 or 0. The sum will be an XOR operation. Why? Because adding 0 and 0 will give a sum bit 0 and a carry bit also 0. If 1 and 0 are added, then I will get the sum bit 1 and the carry bit as 0. If 0 and 1 are added, the same will be repeated. And if 1 and 1 is added, that is equal to 2, and the binary equivalent of 2 is 1 0, where this 1 is called as the carry bit. So I'm writing here, and the sum bit is 0. Now you can see clearly the sum block is, let me write it clearly, the sum block is an XOR operation. XOR of 0 and 0 is 0, or 1 and 1 is 1. 1 and 1 is 0, and 1 0 0 1 will be give 1. So I can write sum as simply an XOR operation, and the carry is an AND operation of this set of inputs. So from this we got a truth table for half adder. So now clearly you can see all the possible cases, that is 0 0, it is 0 0, sum and carry, and all the possible cases. So from this I can get the conclusion that the sum is an XOR operation and the carry is an AND operation. Finally, from that we can write if A and B are treated as two inputs for an half adder, and this can be treated as a whole block, this can be treated as a whole block, then I can write the sum as XOR gate and a carry as an AND gate. So with this basic idea, now let's get started to write a code. And you know that I declared inputs A comma B and the outputs as sum comma carry. So now inputs, I will zoom this. Now my inputs are A comma B. Since these are a single bit data, so no need to write registers, and my output will be sum comma carry. Now I can write this in all the three types of modeling, that is data flow modeling, a behavioral modeling, and a gate level modeling. Now if you are feeling any difficult with these types of modeling, you can comment in the comment section. I will make one more video on that. So first let us write in the gate modeling, or simply I can write as XOR gate. Since I am using XOR gate, output of XOR is sum, the inputs are A comma B, and I'm using an AND gate, so I will write AND, and the output is carry comma A comma B. So these are my inputs. Now I'm going to save this, and I'm going to check the syntax. I'm going to check the syntax here, behavioral simulation, or I have to select this. So I'm going to check the syntax, and oh, it's correct. Now let's write the test bench for that. For that I have to add a Verilog test fixture, and here I'm going to write a test. So click on next. So the test bench is getting added, and here you can see that all relevant things, that range output will be defined as a while in the test bench, and input will be defined as a range, and this is waste, no need, so I can delete this. And from this you can say that uh, initially A is declared as 0, so I will write 1 tick B 0, and I'm writing B as also 1 tick B 0. Now I'm going to take this. So now I'm going to write always, I'm going to change for every 2 seconds my A value as its complement, and always I'm going to change after every 4 time steps my B value as the complement of its value. Now I'm going to check them how they are changing. So I am writing a dollar monitor, and at what time steps they are actually changing, so dollar time. And now I can write the outputs as since they are binary, so percentile B. So the outputs are A comma B. Now I have to give the command that up to how many time steps should it actually perform the execution. So after that I will say that finish. Now here the AND module. Now let me say this. I'm checking the syntax, and here I got an error. So let's see what errors are. Line 42, unexpected defined. So I can remove this. Now let me save. So here I got my syntax again wrong. So line initial dollar amount equal to percentile B and B equal to percentile B. Line 52 expecting dot. Here somewhere I think I missed something, and so let me find errors. That is I think here after we have to remove the comma. So now let's save that, and here I'm going to check my syntax again, and it was correct. So let's see how the timing waveforms are, or the simulate behavioral model for this circuit that we have coded right now, that is for half adder. So let us see how the simulation is. And next we have to check for no, and this is a simulation. So now you can see that for a equal to 1 and b equal to 0, the sum is 1 and carry is 0, and you can verify from the table for 1 and a equal to 1 and b equal to 0, that is sum is 1 and carry is 0. And for all the remaining sets, like here it is a 0 and 1, it is 0 and 1, and for both the cases, if they both are 1, here in this case they both are 1, so sum is 0 and carry is 1. So clearly it is satisfying the way we have given. And now in this you can also see the RTL schematic and the synthesis report, how much time it had taken to execute this circuit, or the timing summary. You can note all the values and the number of gates or lookup tables you have used. You can see that from synthesis report and the RTL schematic. I am just showing for you only for this experiment, and from the next you can see that. See, this is the schematic RTL schematic diagram, and you can go deeper into this up to miniature blocks, and you can check that. So this is the schematic diagram, and similarly you can check the synthesis report also. So that's all for this video, and I think you learned something from the first one. And simultaneous concept is very important to write a code. So if you know the circuit diagram, then it is very easy to write a Verilog code in Xilinx. That's all for this video. Thank you for watching, and subscribe for more.